All right, welcome back to Calc 2. We are going to continue our discussion on differential equations. And this is like a more application, half of the section here. Okay, so let's go ahead and share screen. All right, so find all equilibrium points and determine their stability. So this is what is known as an autonomous solution, or autonomous differential equation. Okay, so what do we have here? We have dy by dx is equal to y x squared minus 1. Okay, it's called an autonomous equation. Okay, the independent variable does not show up in the equation. Okay, independent variable does not appear in the equation. Right, so that's what's going. I don't know why it's called autonomous, but that's what autonomous means. Okay, that the x or the t is not here. Dx, y by dx, it is. Usually in differential equations, it's usually a dy by dt. Okay. So they want to know some stuff like where are the stable points. That is where dy by dx is not changing. It's 0. Okay, so where is dy by dx equal to 0? So that's what we're going to do. We're going to do y squared minus 1 is equal to 0. So we have y minus 1, y plus 1 equals 0. Okay, and we'll go ahead and take a look at that. So we're going to have y is equal to 0, y minus 1 is equal to 0, y plus 1 is equal to 0. So y equals negative 1, y equals 1, or y equals 0. Okay, we have to graph this. Okay, this is a cubic, right? Y times y squared is a cubic. So, well, hold on, let's not graph it just yet. Let's graph something else. Okay, so this is our x, this is our y. Okay, so where dy by dx is equal to 0, right? The slope is now 0. Okay, so the slope is now 0. That's a 1, that's a negative 1. So these are the points here where our slope is equal to 0. So regardless of what the function looked like beforehand, right? Once it gets up to like y equals 1, okay, we're not changing anymore. Okay, so you could have a function that would do something crazy like this, right? And when y is 0, right, we'd have a flat part because the slope has to be 0. So you can't have something that goes shooting off like this because the slope has to be 0. So this is not happening. Same thing over here, right? You can't like all of a sudden start diving down a bit. The slope has to be 0. Up here, the slope has to be 0. You're not escaping this way. Okay. So once it gets to this spot, it's stable because the slope is 0. It's not changing anymore. Okay. So what we're going to do is we'll just kind of dot in what we think the function kind of looks like here. We'll use pink for the function today. It's fine. So here, right, slope is 0. Actually, let's do one more thing before we get to that because I have to know if it's positive or negative in certain places. Okay, so here is our graph. Here's a y, here's a dy. Okay, and we know that at negative 1, 0, and 1, right, dy is equal to 0. Okay, it's a cubic, it's positive, right? The first coefficient is positive, so we know it's going to look something like this. And there's no repeated roots, so we don't have powers of 2s or powers of 4 somewhere. So I know at each 0, it's going to go through. Right? And we'll have something like that. So if we had an x minus 1 squared, we would have, right, it would bounce. At 1, it would have to bounce. Okay, I don't know if you remember that back from college algebra. I know it's been a while, but that's what happens. If you wanted to graph this in your graphing calculators, I have no objection, okay? Because now we're interpreting this graph, we are not trying to graph it, okay? So at this point, your goal here is to interpret this graph. We've already gone through the idea of graphing it. So we could say this is, where's my dependent? So x times quantity x squared, okay, minus 1. And if we go through here, I think we can graph this. Okay, and we might have to zoom in a bit. Zoom in. Okay, might have to zoom in a bit more. Okay, so zoom. Okay, in order to see this. But you could also graph this in Desmos. I mean, you can't do that on an exam, but you know, the idea that you could have a graph of this if you wanted to do that. Okay. So here, right, the graph, the y is, or I should say the dy is very negative. So once the graph falls below 1, right, we have negative slopes. So what I'm going to do is we're just going to have negative slopes after that. Okay. Between -1 and 0, we have positive slopes. Okay. Between 0 and 1, okay, between 0 and 1, we have negative slopes. Okay, and once we get above 1 up here, we have, again, positive slopes. All right, so now when they're going to ask us the rest of the questions, like is it a unstable point or a stable point, right? This line 0 here, right, y equals 0, okay, this is kind of drawing in our x's and keeping them there, right? So whatever's happening with this function, it's coming into this when y equals 0, and they're pretty much trapped. Okay, once they get in here, you're done. You're not moving anywhere else. Okay, this -1, like if y is -1, if I look at what's going on with my function, my x values, right, they can't seem to get away fast enough. Right, that's an unstable point. So as soon as it gets this, if we put something that's anywhere close to -1, right, it's going to slide away immediately. Whereas if we put something close to the x, right, or y equals 0 rather, we are going to slide into this value here. Okay, it's going to attract them all. See what's going on with y equals 1 here, right? Again, you put something on close to y equals 1, it's going to be like two positive magnets. They're just gonna have each other repel. So in other books, that's what this is called, as a repeller. This is an attractor. Okay. If you have a point, this isn't in our book right now, but if you have a point where you're doing something like this and then doing something like that, like if it's above it, it will attract it, but if it's below, it'll reject it, or it'll repel it. That's called semi-stable in your book, and it doesn't matter, right? We could do something like this. Okay, so as long as it is getting attracted on one side and repelled on the other, that's semi-stable. If it's always being repelled, right, that's an unstable point. Okay, you think about people who are unstable with how the relationships are, they push everybody away. And then they have stable, you have stable, and maybe you're not, maybe you like the unstable. I mean, I'm not judging. Okay, but generally stable people are going to attract stable people. Okay, so however you want to think about it, okay, that's mine. We could write soap operas about these people, I guess. But then we'll go from there. Okay, but that's what they're going to ask next. Okay, so let's see here. And notice we never solved this. Okay, technically you can solve this, but the techniques you need to solve it are something called partial fractions. So an engineering Calc 2 person would have, I wouldn't say problems. I mean, this would be a reasonably fun Calc 2 problem for engineers to give, but you know, it'd be a bit of work. Okay, not terrible, but it would be a little bit of work. So we can't solve it, but notice what you did. You did not solve this equation whatsoever. Can you tell me anything about what's going on with the function? Yes, you can. So it's not always important that you have to solve something precisely or exactly in order to know like what's the behavior going to do. Okay. So let's go back to our values here. Okay. So equilibrium points are at -1. Let's not do a point. Let's do a 0 and 1. Let's do a comma 1. Okay. So that should be okay. Check. All right. Now we'll talk about for the least point, right? The smallest one. What statement is true, right? For the smallest point, is this a stable or unstable point here, or semi-stable? Right, it's an unstable point. Get away from me. Okay, so immediately it's pushing the function away from it. So this would be the equilibrium point is unstable. That would be about right. Right. For the second least one, the middle one, okay, that is a stable point, right? That drew everybody to it. Okay, so that would be a stable point. And then back to here, this would be the third least point, the biggest point. That would be an unstable point. It wants everything to go away from it. Right? That's why I kind of like attractor and repeller a little bit more because, you know, like, what's unstable mean? Because to me, like, you know, a semi-stable point kind of looks unstable, like it's doing two different things. Like, make up your mind, right? It's attracting on one side but repelling on the other. So I like the other books that use attractor and repeller, but whatever, this will be fine. All right, so this is the fun part of differential equations, because if inflation grows continuously at a rate of 5% a year, that's pretty high, how long will it take $9 to lose half of its value? Okay, don't round the answer until the end. You might remember these, okay, from your college algebra days. Okay. So what we're supposed to do is we're saying that the change in, so let's go ahead and we'll say y is equal to, y will be equal to its value, okay? And then we'll say, I guess t is equal to time in years, okay? So the change in the value, okay, is equal to negative, I want to say 0.05 for 5% per year times its original value. Okay. So yeah, I want to do something like that. Okay. Yeah, that's what I want to do. Okay. So we have to solve this as if we're a differential equation now. Okay, because they want to know some points here. So we're going to say dy over y is equal to negative 0.05. We'll say t here instead. Okay. Change this to a t. All right. So the change in value is equal to negative 0.05 times the original value. Okay. And what we're going to do is we are going to say something like, I still don't like it. I like 0.95 for value. But, all right. All right. So we're going to have ln y, right, is equal to, oops, I'm sorry. We should just have the negative 0.05 here. Sorry. Negative 0.05. Because all we're saying is the change is equal to negative 5%. Okay, the change is equal to 5%. The rate is negative 5% per year. So you should just have that. Okay. So when I only integrate both sides, right, we have negative 0.05 t. Okay. No, we're okay. That's what. There's no y here. What am I doing? Okay. Negative 0.05 t. All right. Plus some constant. Okay, let's go ahead. E. So we have y is equal to e to the negative 0.05 t. Okay. And plus c up here, because we are making e the base of both sides. Well, we're still going to do this. Negative 0.05 t times c is equal to y. So y equals c e to the negative 0.05 t. Okay. So in year 0, like now, when time is equal to 0, $9 is worth $9. Okay. So y equals 9. So we'll say this is 9 is equal to c e to the 0. Okay. So e to the 0 is 1, and we get c is equal to 9. So let's go ahead and do this. So we're going to say our value is equal to 9e to the negative 0.05 t. All right. And now we want to know, when is it going to be that we lose half of our value? So we're going to write in, what's half of 9? Well, why don't we do this? Why don't we write half times 9 equals 9e to the negative 0.05 t. Okay, we're going to divide both sides by 9. And we end up getting 1/2 is equal to 0.05 t. We got to solve for t. How do we get t down from the exponent position? We take a natural log. So natural log of 1/2 is equal to e to the negative 0.05 t. This business here comes down in front. Why does it do that? Do you remember this logarithm property? Of course you do, because you'll never forget something like that. That's important. Okay, so we have natural log of 1/2 is equal to negative 0.05 t times the natural log of e. The natural log of e is always 1. Okay, so we'll say we have t is equal to 1 over 0.05, okay, times the natural log of 1/2. Okay, let's plug that in and see what happens. Okay, so t is equal to, see if it seems reasonable. Okay, because this is actually the value, this is the formula that economists use. Okay, and so it's going to seem kind of right. It's going to feel like it's going to feel like it's an answer that you can deal with. Okay, so we have 1 over 0.05. Okay, I didn't put a negative in here. Let's go ahead. Second function, insert, put the negative in. Okay. So negative 1.05 times ln of 0.5. Okay, it's 1/2. And I know this is a negative number, so negative times negative will turn back to a positive. Okay, and we get t is equal to about 13.86 years. So we'll say 14-ish years, a little earlier than that. If our 5% remains constant, like that's one thing you can pretty much realize, right? Like if things don't change, then if things don't change, somebody's about to lie to me. That's what's going to happen. Okay. And so we have 14-ish years, right? That's what, 3 presidents. So the inflation rate's going to change or not between then and there. Like, yeah, it'll change. But that's what they're saying if we have constant. Okay. So I wouldn't take this to the bank per se, but yeah, that's what we'd have. And you have to think to yourself, like, does that make sense? Like the value of your $9, the value of your $10 is going to be half of what it used to be in about 14-ish years. Okay, that's a little fast. You don't usually have inflation like this. But by the time, like when you started high school to now, like I don't know what the cost of a Starbucks was when you started high school, and I certainly don't know what it is now, but you guys are going to be a better judge from that. Okay. So it's going to be about half of what you got right now then. Okay. Assuming this is true. This isn't, but if you get like 1 year, like for the value of your money to go into half, like unless you're talking about like post World War I Germany kind of thing, like there's hyperinflation. That's not even, 5% is not hyper. It's got to be a lot more. But you got to talk about like a seriously dysfunctional economy when you're going from like my $10 was worth $10 today, and in 6 months it's worth $5. Like something bad has happened. All right. So if you're getting weird numbers like this, like they should make sense to you. If they don't, like check something out. Like, what if you didn't set this up right? Did you have a negative or a positive? When it said, this is the most common mistake, when it says 5%, they say, a lot of students do dy by dt is equal to -5. Okay. This is hyperinflation because this is 500%. Okay. So realize that there are mistakes that you can make with this, but generally you're going to look at this and you're going to say, wait a minute, I've had money for 10 years and it's not worth half of what it used to be. Okay. So same thing with bank accounts, with interest accounts. You have no idea how many people do the 5% like that, turn it into 500%. Like, here's a word of the day for you. USury. This is charging too high of a percent interest. So if you ever find yourself compelled to walk into a check cashing place, please stop. What they are practicing there is called USury. Okay. Don't yell at the clerk. He or she doesn't know anything. You can yell at the owners. Okay. All right. Next. Okay, elasticity of demand. These are fun. Okay. They do this, they actually have this in your Calc 1 class. I think we don't teach it anymore, but it is in your like in applications of differentiation, like back in chapter 3 or 4 or something like that. But we have a demand function. We say E is equal to -P over Q times dQ rather dP. Can we change that? So people who are economists, they do lots of research on what elasticity is. It is pretty much saying like, what's the, if the price changes, what happens to the demand? And you usually expect, like, if the price goes up, the demand goes down, right? So if the price of diamonds goes way up, say you're the person you want to propose to, like we might have to wait, to get the diamond ring that you really wanted, or not at all. Okay. It fairs, like if you go to a fair, like the price of cotton candy goes way, way up. Like if that's your one fair in a decade, you might buy the cotton candy even at that price. But if you go to the fair every year, the price of cotton candy is huge. Like maybe I'll skip it this year. I don't need to have that. Okay. But if you're looking for a graduate degree in economics, one of the things they do is like they ask like, hey, what's the elasticity of like heroin? And they have to go through and interview people like, what if the price of heroin doubled? Would you still buy it? Yeah. What if it tripled? Yeah. What if it was 10 times? Yeah. So elasticity for a lot of drugs is it's what they call inelastic. You'll buy it at any price. They don't care. All right. Enough of that. Let's see. Find the general equation. Q is equal to FP. Okay, so Q is our dependent variable. P is our independent. Okay, and E is equal to 11. So I guess E is a constant. Whatever they're studying, E is constant. I have no idea if that's a high number or a low number. Okay. So we're going to say, since E is equal to negative P over Q, and then we have dq over dp, we're going to separate these out. We're going to say something like E times P, that's a constant, dp, or at least we're going to treat it as one, okay, is equal to 1 over Q dq. Okay. Oh, no, we're not. We're going to say this is E over P. This is 1 over P dp. Right, because it was on the upstairs over here. If I want to send it to the next side, right, it's going to go down there. Okay. So let's go ahead and integrate both sides and see what happens. So we have integral, right, of E times 1 over P dp is equal to integral 1 over Q dq. All right, so this is going to be E times the natural log of P is equal to the natural log of Q plus, and they insisted that we actually integrate this out with respect to C being ln C. So we're going to say this is ln C. Okay. Now, do you remember your rules of logarithms? Of course you do. Okay. That's a rule of the logarithm. Okay. I say that like I really expect you to memorize this, or how I expect that I'm reminding you of this, and you'll keep this in your head when you're going through your homework and when you're doing your quizzes. I do not mean that you would have memorized this from like 2 years ago, and of course you would just know it. Okay, I mean you should, but you know, I know very well that I'm reminding you and not anything more. So even though it may sound like I'm expecting you to have this memorized, you were not told you might need this again. So I'm telling you now, you might need this again, but I'm going to remind you as we go through. Okay, so this is E. Oh, this is actually going to be P to the E. Okay, this is going to be P to the E. ln, okay, is equal to this. And of course, you know, we just did this from the other day, or from the last chapter. The ln of a to the r is equal to r times ln a. This goes backwards too, so if I've got E times ln p, then we can turn an ln of p to the e. Okay, so what I'm going to do next is I'm going to take E as the base of both sides. We're going to unlogify things. So E to the natural, don't use that word, by the way, that's a word I made up. So other people, if you do that, people may decide like, what are you doing? Okay, you're not saying it, you're saying nonsense. So this is C times Q, right? C times Q. And then we have to, I think we have to solve for P. No, we don't. We're solving for Q. We're solving for Q. Okay, I may have done this backwards. We'll see. Okay. So Q is equal to 1 over C, P to the E. We'll hope that that holds. Okay. Q is equal to 1 over C, P to the E. Okay. Oh. And the general equation. They didn't give me enough information for figuring out C here, so I think we're stuck with this. One hope. That is incorrect. One, I forgot a negative sign. Okay. Let's go back and fix this. E is equal to negative. Yeah, I know, baby. Okay, let's see here. P over Q. P over Q. She's in heat, I'm sorry. dQ dP. Okay. So we're going to say something like this is E over P, okay, dP is equal to negative 1 over Q dQ. All right. So integrate both sides. Maybe not much changes. So we get E ln of P is equal to negative. All right, and we get ln of Q plus ln of C. And they want this thing in terms of Q. Q equals. Okay. So let's see here. This is going to be ln of C minus ln of Q is equal to E ln of P. This is ln of C over Q, same idea. This is ln of P raised to the 11th power, okay, because E was 11. We're going to logify here, so this is P to the 11 is equal to C over Q. Okay, so here we have it. We have Q times P to the 11th is equal to C. Q is equal to C over P to the 11th power. Okay, let's see if that gives us any better choices here. Okay, so this is C over P to the 11th. Okay, so what I have written, it is. All right, that's what they wanted. Okay, don't forget the signs. That's an issue. Okay. Too late though. How many choices do we have left? This is what, number 12? Four more. Oh. Okay. All right. Let me show you how to do this one. Okay, it's not going to be that bad, but if you've not done it before, you won't know. So hopefully you have a TI 84 calculator. 84s are a little bit better. You're going to have a slightly better menu than I am, but we are going to go to our stats menu. So if you've had statistics, we're going to go to our stats menu. We are going to edit some lists, okay, which means we're going to type these numbers in. You're going to go to, after we type those numbers in, we're going to go to stats. We are going to go to logarithmic ln reg and hope for the best. Okay. So let's go ahead and give myself some lists. So we're going to go to stat and edit, and we're just going to put all the days in one column and everything else in another column. Hey, what do you know? A global pandemic. Who would have thought? 74, 79, 95, 136, 151, 162, 162. Okay. 180, 210, 222, 234, 263, 273. All right. We'll go over to this side, and we're going to go 29, 67, 123, 156, 315, 538, 1090. Should be so lucky, right? 2264, 2830. Okay. 3789, 89. Oops. 89. Okay. 4242. Okay. 4524, 6903, 8464, 10571, 10571. Okay, 14. Oops, I don't want that. Oops. Jeez. Okay. All right, sorry about that. 10, 5, 7, 14, 508, and 14 to 63. And that's everybody. Looks like that's everybody. Good. So we're going to go to stat. We're going to get a calc. Okay. We are going to go to LN regression. Okay, that's what they wanted, was linear regression. Okay. Enter. See, if you have T84, they will tell you. Okay, they will tell you. Stats, calc. Okay, that's exponential regression. Oh, there's logistic regression. We'll use that because that looks a little bit better. Okay, and then we're going to do is say list 1, comma, list 2, and I think that's going to do it for us. That's going to think. It didn't instantly come back with an error, so that's helpful. Okay. They say calculator for logistic regression quantities. Okay. In any case, you know what this thing is supposed to look like. It's increasing, right? So it should look something like this one. We'll see what D is. Okay. Like I said, in 84 is going to be a little bit better. There it is. That's the model for logistic regression. It's a little bit of algebra. Okay. We are going to go back to, if I could read this better. I'd like to graph it. Oh, let's see. I'd really like it to graph. Is this stats plot? Is that what that is? There it is. Look at that. Stats plot. List 1, list 2. All right. That looks good. Okay, let's say graph. Let's see what that does. That did not do it. All right, I want this one. Enter. On. I don't know what they want us to do. I can't go down anymore. It's not doing anything. Let's hit that one and just say plot. Nope, not doing it. Don't want that. Don't want that. Don't want that. Oh, jeez, I don't want any of that. I just want this one. How can we do it? Okay. Not really sure. I would use Excel. Okay. That's what we have. Plots on. Let's see. Oh, jeez. I'm not going to keep going with this. I didn't think it. It's just I don't know what to do with it. So I would use Excel. I don't know how to, or I would look up on YouTube and say, how do I use my calculator to 83 to graph statistics graphs and do something with that. So I don't know. I'm not gonna worry about it. Okay. I suspect it's this one. Okay, because that's what logistic curves generally look like. So we're going to go with that. Yeah. Thanks. All right, maybe this one. It went down a little bit at the end. So maybe this. Maybe this one. All right, I guessed. Okay. Is it an appropriate function? Yes, the logistic model should be used for a cumulative count. They do show a clear thing for the logistic curve. Any model is appropriate as long as the fit to data is good. That is not true. Regression does not want you to do that. Regression wants you to pair the model. Oh, we are going to fight. Okay. All right. I'm going to leave it. Okay. But that's how you do it in your graph. Again, I would go with Excel and do it that way. And then I am not saying that any model is going to work because that is not what you're supposed to do. You're supposed to have like an idea of what you're doing. If you don't have an idea, you go ahead and use a linear one and say, well, it's got, so when we pick the most basic relationship we have. Okay, so that's what you do. I'm going to go ahead and stop this one before it gets to more of a disaster. And I have really messed you guys up. But again, we're going to solve this differential equation. Okay, what it's going to do at the end, sorry, I will say this. You should notice, right, that we're going to get a dy over a y is equal to a k dt. When we integrate, okay, we're going to get ln y is equal to kt plus c. On logify, we get y is equal to e to the kt times e to the c. And we have y is equal to c, because e to a constant, times e to the kt. And again, you should have a whole host of college algebra problems that will come flooding back to your memories once you've started that, okay, to be able to do unlimited growth. All right, I'm going to stop there and let you guys have this one. All right, next time.